What's the best way to measure the density of an unknown liquid? In this video, I'll show you several laboratory methods for determining it. We'll use a hydrometer, a pycnometer, an equal arm balance, and a Mohr's balance and compare how each approach works. By the end, you may understand multiple ways to measure liquid density and know when to use each method. Let's get started. The easiest way to measure the density of a liquid is to use a hydrometer in a tall graduated cylinder. The hydrometer must float freely and must not touch the bottom of the container. In this case, we are measuring distilled water. The hydrometer reading shows that the density of distilled water is approximately 998 kilograms per cubic meter. To be able to compare it with its tabulated value, we measure the temperature of the liquid. We insert a thermometer into the graduated cylinder and read the value from the scale. In this case, the temperature is approximately 24.0 degrees Celsius. The smallest scale division is 0.5 degrees Celsius. In the second way to measure the density of the unknown liquid, we measure the mass of the empty, dry pycnometer using either the equal arm balance or a digital scale with a precision of 0.1 grams. To measure the mass of the liquid in the pycnometer, we carefully fill it with a measured liquid, in this case, distilled water, making sure not to wet the outside walls. Then we insert the stopper. Excess liquid will overflow. We wipe the pycnometer dry and weigh it. The mass of the liquid in the pycnometer is then equal to the difference between the mass of the pycnometer filled with the liquid and the mass of the dry pycnometer. For correct filling, the liquid level without the stopper must reach at least the neck of the pycnometer. After weighing, we pour the liquid back into the original container and close it. The principle for determining the density of an unknown liquid is based on knowing the density of a reference liquid, for example, distilled water at a given temperature, and being able to measure the mass of both the known and the unknown liquid. The density of the unknown liquid, rho unknown, is then given by this relationship, where the known liquid may be distilled water and the unknown liquid may be, for example, ethanol with an unknown level of dilution. The volume of both the known and the unknown liquid is the same during the measurement because both liquids are measured using the same pycnometer. In the third way to measure the density of the unknown liquid, we first measure the mass of a submerged object, in this case, a small cylinder. Its mass can be measured either by using the equal arm balance or a digital scale. To know how to use an equal arm balance, see my video titled How to Use an Equal Arm Balance, Measure Mass, Step-by-Step Physics Lab Tutorial. We neglect the mass of the wire because it will not be fully submerged in the liquid. To measure the mass of the object while submerged in the liquid, we use a stand and a graduated cylinder filled with the liquid. The cylinder should not be full to avoid spilling during handling. After submerging the object in the liquid, we add weights until equilibrium is reached. In this way, we measure for a given liquid the difference between the mass of the submerged object and the mass of the liquid displaced by that object. In fact, we are measuring a mass corresponding to the difference between the gravitational force acting on the submerged object and the buoyant force acting on it. In this case, the difference between the mass of the submerged object and the mass of the liquid displaced by the object is approximately 40.6 grams. The smallest weight used has a mass of 0.1 grams, so the measurement uncertainty of this mass difference is 0.1 grams. But why do we measure the difference between the mass, mc, of the submerged small cylinder and the mass of the unknown and known liquid displaced by that cylinder? Because we can then use this relation to calculate the density of the unknown liquid, rho unknown. M unknown is the mass of the unknown liquid displaced by that cylinder, and M known is the mass of the known liquid displaced by that cylinder. V unknown is the volume of the unknown liquid displaced by that cylinder, and V known is the volume of the known liquid displaced by that cylinder. Both volumes are the same because they are equal to the volume of the small cylinder, which is submerged completely. Notice that the first equation was divided by the effective gravitational acceleration. Also note that the buoyant force is equal to the product of the effective gravitational acceleration, the density of the liquid, and the volume of the liquid displaced by the submerged object. And finally, in the fourth method for measuring the density of the unknown liquid, we use a Mohr balance. First, we balance it in the air with the object of mass m. In this way, we compensate for the effect of the effective weight acting on this object with mass m. We then submerge this object in a liquid, first in a known liquid and then in an unknown one, and measure only the buoyant force acting on the submerged object, because the initial balancing compensated the effective weight. When measuring in distilled water, we use 3 riders to balance the buoyant force acting on the submerged object: a 10-gram rider, a 1-gram rider, and a 0.1-gram rider. The effective weight of the 10-gram rider has a lever arm of length 9d. The effective weight of the 1-gram rider also has a lever arm of length 9d, and the effective weight of the 0.1-gram rider has a lever arm of length 6d. The buoyant force has a lever arm of length 10d. Therefore, the following equation applies, where GEF is the effective gravitational acceleration, rho liquid is the density of the liquid, V object is the volume of the submerged object, and D is the distance between the 2 suspension points on the right arm of the Mohr balance. Since the submerged object is manufactured to have an exact volume of 10.0 milliliters, we can rearrange the previous equation to obtain this formula for the liquid density, rho liquid. However, this equation is strictly valid only if the Mohr balance is perfectly accurate. In practice, it usually is not perfectly precise, so we must also measure the density of a known reference liquid and compare it with its tabulated value. We then use the ratio between the tabulated value, rho ref known, and the measured value, rho known, to correct the calculated density of the unknown liquid, rho ref unknown, obtained from the measured value, rho known. For the distilled water used in this video, the tabulated density value is, for example, 998.5 kilograms per cubic meter. When measuring in a liquid of unknown density, in this case ethanol, the rider positions are Y1 equals 8, Y2 equals 4, and Y3 equals 1. And that's how we measure liquid density using different laboratory methods. If this video helped you understand the process more clearly, make sure to give it a thumbs up and subscribe to the channel for more practical physics experiments. Thanks for watching, and I'll see you in the next video.